afternoon. So we continue our discussion on boundary layer.
عليكم السلام دكتور.
So I share you this slide, and this slide also can be downloaded from my website. So here it is about to share with you the idea how Navier-Stokes equation being used. Okay, I'm sorry. Okay, so this is for the recording one. So in this slide, I would like to share you about how Blasius used the Navier-Stokes solution to start his calculation, because previously I show you the calculation of Blasius. So it has eta and so on and so forth. They have the combination of certain parameters. So it is actually I would like to explain it in simple in this slide. So it starts with the Navier-Stokes equation. So because to make it simple, we just use the x component Navier-Stokes here. Okay, so and then we only start with a 2D laminar boundary layer. So means it could we could neglect the effect of the width of plate. So this Navier-Stokes equation you could get this equation from the previous notes. So this is the Navier-Stokes equation. So as I said previously, when to solve problem using Navier-Stokes equation, you need to list all the assumption, and then it makes your Navier-Stokes equation easier. You could cancel parameter that not really influence the calculation. So first we assume that the flow is laminar, so which is a steady flow. So that's why in chapter 5 question, we have the turbulence percentage. So means that because normally we assume that free stream velocity is steady flow. Okay. So that's why we take du dt is equal to 0 here. So and then it is only two-dimensional. So the value of z, the velocity component of w is 0. And the gravity is not acting on x-axis, so we take g is 0, and because the z is not axis, so du dz is equal to 0 now. So and then our Navier-Stokes equation will become like this one, and then please get alert that this is the kinematic viscosity, not the velocity of v. So and then we could write this one. So and then Blasius actually used the idea of similarity to solve the problem, or to comes out their parameter, to comes out his parameter to do the numerical works, to have the table. Okay, so for instance, so this is the non-dimensional variable. So we have we learned about this previously, especially for x and y, and also for the u. So are you familiar with this term, except of these two? Okay, so so the pressure here is actually it's come out in ideal flow when we have a circle here, a circular object, a cylinder. So when we calculate this one and so on, I hope you could look back into your ideal flow and notes. So we calculate the pressure at point here, and at this point, so we have a stagnation point here. So we could calculate this one, and finally we could calculate the pressure by using the Bernoulli equation. Okay, please look back the ideal flow notes. So and then we could get the CP, the coefficient of pressure. Coefficient of pressure is actually this term, P1 minus P1 minus P2 over rho U square. Okay, that is the one. So and then the Blasius propose these non-dimensionless. So V times L over U delta. So we are looking for this one first. So this I'm not going to calculate this one because it has another reason. Okay, but if you want to see this one, it is actually the CP, the coefficient of pressure. Okay, so Blasius start with this idea. So let's say we have a wall like this. So and then we assume this is the x-axis and this is the y-axis, and the delta is about what is distant in y-axis, and the velocity of capital U here, the free stream velocity, is actually parallel with x-axis. Okay, at the same time, we have u component velocity at x-axis and v component velocity at y-axis. So from this one, Blasius says that any combination should fulfill the continuity equation. So from here, Blasius proposed that U over L mean the length of the plate here. Okay, U over L must have certain relation with V over delta. So this is the assumption of uh, the assumption of Blasius, because it some kind of similarity. Okay, it is similar if we are looking the capital U and the total length with the velocity V and the thickness of delta and the boundary layer thickness. Okay, so because the relationship is not confirmed yet, so whether it is 2 times, 200 times, or 0.5 times compare, and so on and so forth. That's why in many textbooks, they will write as U over L tilde V over delta. So this symbol is tilde. So it sound, it's give ideas of have relation between this and this, or you could say that it has equivalent relation between U over L and V over delta. Okay, something like that. It's not equal. Okay, because it's not being calculated yet. Okay, so and then uh, Blasius says that in non-dimensional, so this is our non-dimensional, we must know that the units is unity. There are no units. So U over U, so the unit can be cancelled. Also Y over delta, X over L. So means that the value from this assumption must be unity. Must do not have any do not have any dimension, any units. So Blasius proposed, okay, let's say that we have some equal here, U over L equal V over delta. And then we could write if it's unity 1, so it is equal V over L over U over delta. So we have VL over U delta. That's what Blasius proposed. So V star there is V over L. So over U, V times L over U times delta. So this is the idea of Blasius, the idea of similarity. So now what Blasius did is Blasius tried to get what is actually the relation, what kind, the basic idea to get a guide of what equation, or what times what divide by what can is the idea of the boundary layer. So Blasius start to do its similarity, the similarity or non-dimensional or dimensionless uh, uh, theorem or something like that. Everything is the same. So I think you already know how to solve this one. So I just do a quick one. So we replace everything here. So we have u, du, dx, and so on and so forth. So we replace everything. So and then we rearrange the term. We multiply each term with L over u square. And finally, we get this one. Okay. So and then from this non-dimensional parameter, so we found that there are no extra parameter for this one. But we have this nu over ul and also this one, nu over ul times L over delta square. And Blasius actually take this parameter for his study, because this parameter, why he not take this one? So this parameter didn't have any delta. So means that he tried to get correlation he start to do research about the boundary layer thickness, but means that he need to start with something that has the terms delta here. So Blasius used these terms, okay, for his study. So he's right as this one. So and then again, because this is non-dimensional, so means the unit cannot be there. So again, Blasius says that the nu over ul, L over delta here must be equal to 1. Okay, so it is actually not equal to 1. So it is must have relation with 1. So it's not use the symbol of equal here. Okay, so it not use the equal, so it use the tilde. Okay, so and then from here, okay, so from here, I think we could play around the value. So we have nu over we have nu, we have ul, and then we have L square over delta square here. And then if we rearrange this one, okay, you could assume it's as the equal for the tilde sign. And finally, we could rewrite as this one, because we assume that Reynolds number is ul over nu. And then we have delta L is tilde 1 over Reynolds number. And then we could write as this one tilde delta tilde 1 times L over square root Reynolds. So means delta here have relation with 1 here. It's yes, it's 1. But in this case, we could assume that 1 here is the certain numbers times L over square root Reynolds. So that's why when Blasius do all the calculation, so he satisfied when he get delta is equal to 5x over square root Reynolds, because this is actually the equal one, the final equation. But the overall, the first assumption that is tilde, and I'm sorry, a delta tilde, I mean have relation with numbers times L length. So in this case, x over square root Reynolds. Okay, can you get it? The idea of this one. So then the discussion about the pressure in the boundary layer. Okay, so a few assumptions is first, the pressure across boundary layer is nearly constant. So this means that if we have 2 points, x1 and also x2 here, we found that they are different in terms of pressure from point 1 and point 2, because the velocity is different, then the velocity is different, then the velocity the pressure is also different. But we make Blasius make an assumption that pressure at the same location, mean pressure for x1 here is almost constant. So mean pressure at point 1 is constant. Also mean pressure at point 2 is different, but along the y-axis is constant. So it simplifies the equation that dp dy is equal to 0. So and then because the pressure at point 1 and the pressure at point 2 here cannot be neglected, because the obvious one is the velocity is become higher and higher. I mean there are changes of velocity. So it is okay for us to calculate the pressure in experimental by using this one. So if we do we install the pressure tab or the YouTube manometer here, so you will find that the pressure is different between point 1 and point 2. However, we assume that pressure at point 1 at y here will constant. Okay. So and then from Bernoulli equation, we have, I think you already know, Bernoulli equation P over rho G V square over 2G plus Z is equal constant. Okay, but for boundary layer, we could ignore the existence of Z, because we assume that the different height in boundary layer is actually very small and it is not worth to being counted in our calculation. So the Z is neglect. And the G is bring to the right hand side. So we have P over rho plus 1 over 2 U square constant. So and then here we bring the U to the right hand side. So we have a negative symbol here. And then we differentiate these terms. So we differentiate with dp dx on the left side. So we have uh, P is gone, so we have 1 over rho. And then here we have a negative 1 over 2 U square. And we differentiate into du. So U square will become 2U. Okay, 2U negative over 2. And we have du dx here. So this is the theoretical theoretical differential. Okay, so it means that we still keep the du dx here because we differentiate dp dx and du dx. So the u is the 2 here is can be cancelled, so it is become negative u du dx. So why Blasius propose this derivation? Because okay, so he want to neglect the terms of pressure inside his equation because it will complicate the equation. If you see the boundary layer equation that you know right now, the calculation of delta, the calculation of theta, the calculation of delta star. So we are only dealing with the velocity. There are no parameters of uh, pressure. Okay, that's what actually the first intention of Blasius, not to use the pressure, because if we need to use the value of pressure, so means you need to uh, take any data about the pressure. So that the first assumption. And in real application, Blasius found that if we do experiment on the flat plate, okay, so the pressure gradient is not so much different. That's why if you read about boundary layer, so you will find that it says that is with zero pressure gradient. So it's referred to the flat plate. And then I think in my notes I give you a notes about pressure gradient when flow around a curved surface. When flow around curved surface, so you will have a pressure difference, then the separation occur. Separation will not occur on the flat plate. Okay, that's why Blasius try to neglect the pressure, because in real application actually the pressure difference is not so high, so it cannot create anything. Okay. Okay. However, Blasius still believe that pressure at point 1 and pressure at point 2, as we see here, is different, so it must be calculated. And the relation of pressure and velocity can be seen in Bernoulli equation, and Blasius rearranged the velocity, the relation, and we have this one, and then finally we could substitute in our terms. So this is the Navier Stokes from the Blasius. So we simplify all the things. We replace the term of here 1 over rho dp dx with this term. So when negative meets negative, so we have positive now, and then we can ignore the term of this one v du no d square u dx square. So the reason is, okay, the viscosity, the kinematic viscosity is too small. So sometimes we have negative 3, negative 4, negative 6, and d square u dx square means you differentiate the velocity along the x, okay, twice. So means the value will become smaller and smaller. So means, and okay, so the value becomes smaller and smaller. So then when the small value times another small value, and the sum will be too small. So Blasius says that, okay, we neglect this one. So we could reduce the term. So we du dx will be neglect. So now our term will become like this. So this is the common Navier-Stokes equation being used of Blasius in his calculation. So it is called sometimes the boundary layer equation. So this is the continuity equation actually. So and then this is the momentum equation. In certain textbook, they will use momentum equation or some kind of Bernoulli equation, mean equation that shows you the movement of fluid. So and then to solve this one, so Navier-Stokes, sorry, I'm sorry. Blasius, again, they use the boundary condition. So the boundary condition is, okay, they take the control volume here, the control area. So and then they will take as this one. So mean U and V at equal at 0. So the Y is equal to 0. And if U is equal to capital U, mean the free stream velocity, the Y is equal to infinity. And sometimes in another, if you have this boundary condition is actually for the general terms. Okay, so in our study previously, I show you, so U equal to capital U at Y equal delta. Okay, so and then the U equal to starting Y is at X as starting Y here is actually the the terms to tell about the condition at somewhere here, mean at certain value of Y, at certain value of X, so you will have a certain value. That's why it's written as X starting here may not be 0, may or may not be 0. So means that if you are talking about this point, so you have the value of X and you have a value of Y. That is the spirit, the basic meaning of that statement. Okay, so now we are try to see what is the major step takes by Blasius to fulfill their calculation. So the assumption is the flow is steady, incompressible, and two-dimensional in XY plane. The Reynolds number is high enough that the boundary layer approximation is reasonable. So the number 2 here is actually saying that it is not a very low Reynolds number. Okay, so because low Reynolds number will give a creeping one. So that's why we call it as a creeping flow. So the boundary layer remains laminar over the range of interest. So when we assume that everything is laminar, because in reality, it is not easy to control to get a very, very laminar flow in your experimental rig. So and then there are no pressure gradient remain in the X direction boundary layer. As I said, they assume that in flat plate, so there are no pressure gradient. So and then we could write, because there are no pressure gradient here, so our equation will become like this. So the terms of pressure gradient, whether it is changed into U, so it will become into 0. Okay, so in the okay, in previous slide, so why Blasius try to replace the the terms of pressure, because part of the experimental conducted by Blasius is actually on the curved surface, because Blasius also, as I said, if you see the notes in chapter 5 and everything, so there are a lot of researchers actually predicting the transition, separation and so on. So they actually do in various type of object and so on. So on that time they will use the pressure and so on. So okay, so blesses. So now we move into the flat plate. So we reduce the pressure gradient. So and then this is the boundary condition as I explained previously. So you may assume that Y equal of delta it sometimes can be replaced with Y is actually approach to delta at U equal to U. Okay, so and then again, so Blasius used the idea of similarity. So and then they try to make sure. So why Blasius like to use the idea of similarity? Because first, it will neglect that will the effect of unit is not there. Okay, so what is the effect of unit? For example, if you're talking about 1 meter, So the effect of 1 meter is actually not similar with the effect of 1 centimeter, because you have units, so mean you need very careful to talk whether it is one, but the unit give you uh, an extra new ideas about that one. Okay, that's why Blasius doesn't want the units, so they just say that okay, the length is L and so on and so forth. So they do the similarity works actually, and finally, okay, they comes out with the symbol of eta. So I make it easier here. So do the similarity, and then they propose the work of eta. So eta here is equal to y u over nu x. So again, if you see our textbook, viscous fluid flow. So in viscous fluid flow, they use y square root u over 2 nu x. Okay, so the calculation is actually the same. Okay, but you need very careful when you read the textbook with this equation. You will find that eta is equal to 3.5. When you take this equation as my notes, so you will find that from the table, the eta will equal to 5.0. But both of these assumption is, okay, you will get delta is almost 5x over square root Reno. Okay, 5x is the most common one. Okay, but sometime in tutorial, I think I will show you the if what happen if we go to the very precise of 99%. Okay. So and then Blast use this idea and start from this. I think I already explained it in tutorial. So when we solve Blast ideas, so to simplify that, so eta is actually can be reflect of this one, and at the same times the u over u here is reflect as f prime. So f prime here also can be written as f prime eta, mean f prime to the function of eta. So and then the it has equation. You could look back for in the previous notes. So we have f double prime plus 2f triple prime, something like that. So and then Blasius used the popular Runge-Kutta numerical techniques. Okay, so and then it can have a table like this one. So here the basic assumption is written like this one. Eta is the similarity variable defined in equation 2. So you could refer back after this. So this is equation 2, equation 3 later on. So, and then a function of eta is solved using the Runge-Kutta numerical techniques. So and then f is proportional to the stream function. F prime is proportional to the x component of the velocity of the boundary layer. So u over u, and f double prime is proportional to shear stress. And all of this, so in easy way, Blasius will give all the parameters and so on and so forth. So, and then he could come out with this table. So, and then from this table, the idea is, okay, I will show you, okay. The idea is we still stick to the basic definition of boundary layer, which is U is equal 99% of capital U. So it can be written as U over capital U is 0.99. So we focus on the column of U over U, which is F prime here. We find what is the nearest point to 0.099. So here we have 0.091 and 0.97, 0.991 and 0.979. So that's why in common textbook, they will take 5, eta equal to 5 here. Okay. So, and then, but, okay. So this is the one of the plotted data of Blasius. Okay, we need. Okay, so this is the the one. So let's say if we want to calculate very precisely, so we take f prime or u over u is 99%, so we can calculate interpolation between these two numbers 5 and 4.5 because we have these two value. So you could do the interpolation here and you could get eta is equal 4.91. So and then we equalize 4.91 equal u over nu x delta. So and then so we have y here. Okay. So okay, please remember this one. So the equation is actually y square root u over nu x. Okay. So y is equal to delta because y is now become a boundary layer thickness and eta is 4.91 based on the table. And then we could find is delta over x is 4.91 over Reynolds number, or delta is equal 4.91 x square root Reynolds. Okay, so and then I hope you could try to do this one by using the idea that we learned previously. So we get tau wall here is 0.332. So and then the local drag coefficient C with a small d here is 0.664. And then we could calculate the value of CD. So CD again can be calculated by using the 2 theta over L. So I think I mentioned this in a previous note, so you could get the value of CD. So it is actually almost equal to as I shown in the previous notes.